Okay, so can everybody see the slides? And also the transition, is the transition okay?
I can.
Okay, great. So let us continue with the VC dimension. Right? In the last lecture, we introduced the concept called VC dimension, which is based upon shattering, right? So shattering is just telling us the relationship between a set of functions h, um, h and a set of examples or data points s, right? We say our set of functions h can shatter this particular set of examples s if and only if for every possible labeling scheme on the examples in S, we can find a corresponding function in H that gives the correct prediction of every label. So basically, you can enumerate all possible labels over S. And as long as we can ensure that for every labeling scheme, we find we find a function in H that can give a perfect prediction of those labels, then we can claim that H can shatter S. Right? This is also how usually we examine if H shatters a particular set of data points S, right? So H is also referred to as hypothesis space, right? So the shattering actually activates the capability of our function set in predicting a particular number of the data points. Right? That's why the VC dimension is defined based upon this shattering, right? So um, the VC dimension for a hypothesis space H over some instance space X. Right? X is the whole space that includes all possible um, inputs for training on test, right? Is defined as follows, right? It is actually the size of the largest finite subset of X that can be shattered by H. Um, if there exists any subset of size D that can be shattered, then we can claim that VC dimension is no less than D. So here is some kind of thing you might feel uncomfortable or feels kind of unnatural, but this is how the VC dimension is defined. So if when we claim VC dimension is at least D, it means that uh, there exists some subset of size D that can be shattered by H, rather than any subset of size D must be shattered by H. As long as you can find one particular set of data points of size D that can be shattered by H, then we say the VC dimension of H is no less than D. Only when not any subset of size D that can be shattered, then VC dimension is less than D. So take the linear classifier in two-dimensional space as an example, right? So we know that we can start with 1 point, right? So for we can pick any 1 point, right? So we know that the linear classifiers can shatter 1 point, right? For 2 points, we pick 2 points, and we know by enumerating all possible labels of those 2 points, and they can be classified by a corresponding function in the linear classifier space, right? But for about 3 points, right? So if we intentionally place the 3 points on one line, right? Actually, this particular 3 points cannot be shattered by linear functions. To see these points, you can just label the first and third point as positive, and the middle negative. We cannot find any line to separate two positives from one negative. However, this does not mean the VC dimension of linear classifiers in two-dimensional space is less than 3. Why? Because I can find another 3 points right in this two-dimensional space such that they can be shattered by the linear classifiers. Right? Since we successfully found a particular set of 3 points that can be shattered, then the VC dimension of linear classifiers is at least 3. And then we can proceed to the 4 points case. And in the 4 point case, actually, we can find that no matter how you place the 4 points, right? They can be placed in 1 line, 2 lines, or whatever, right? For any particular position of 4 points, they cannot be shattered by a line. So we end up with the conclusion that the VC dimension of linear classifier in a 2-dimensional space is 3. Okay, so this is just a review of the definition of VC dimension. Is very important for everyone to understand that concept, and also to check some simple hypothesis space, calculate the VC dimension, right? And then we list the VC dimension for a few commonly used classifiers like half intervals 1, intervals 2, half spaces in the plane, which is actually linear classifiers in a 2-dimensional space, which is 3, right? And in general, linear classifiers in D-dimensional input space is D plus 1. If you take D to be to 2, it actually returns the example we have discussed, right? The neural networks, the VC dimension is number of parameters, the 1 nearest neighbor, the VC dimension can be infinite, right? So, and again, let us look at the motivation of the VC dimension, right? So the motivation of VC dimension is to describe or characterize the expressiveness or the complexity of your hypothesis space. So you can view as a counterpart of the log size of hypothesis space for the finite hypothesis space. So we know that in our computational learning theory, when we derive some sample complexity bound, generalization error bound, right? We use log of the size of hypothesis space H to indicate the complexity or expressiveness of the hypothesis space. Right? We know that the number of samples or the bound of the true error is partly determined by this complexity or the expressiveness of the hypothesis space. Right? Similarly, for infinite hypothesis spaces, which are even more common, the sample complexity bound, generalization error bound, they are both determined by the complexity or the expressiveness of your hypothesis space as well, right? Even your hypothesis space is infinite, right? But their complexity or their expressiveness can be different, right? So that's why we need a finite measure of such complexity for infinite hypothesis space. Right? That's how the VC dimension was invented, right? And then we listed the result, right? Suppose our hypothesis space is infinite, right? In consistent learning case and agnostic learning case, what is our sample complexity? What is our generalization error bound, right? We actually have such kind of results, but of course, the derivation of those bounds will be much more complicated than what we have gone through for the finite hypothesis space. We'll not cover those derivation, right? If you're interested, you can look into any theoretical book about computational learning. But anyway, the final result is kind of like consistent in the form as in the finite hypothesis space case. Right? So if your classifier can always guarantee a consistent hypothesis with the training examples, meaning that your training error is always 0, right? And then if the number of training examples is bigger than this guy, we claim that with high probability, at least 1 minus delta, your learned hypothesis has the true error less than epsilon. So I have the same structure to describe the sample complexity, right? But the bound itself has a little bit change in terms of the coefficient and forms, right? So in this bound, the logarithm size of h, right, is now replaced by this 8 VC dimension of h times logarithm 13 over epsilon plus this 4 is the actual coefficient on that, right? But anyway, it reflects some similar structure to the previous conclusion, right? And also, it also, again, justifies the Occam's razors principle, right? We say that the more complex your hypothesis space, meaning that your larger the VC dimension, you will need the larger number of training examples to achieve same error level under the same confidence level. Right? And for the more realistic agnostic learning, right, we derive a similar bound to the finite case, where the true error for any fixed number of training examples, right, we can claim that with high probability, at least 1 minus delta, the true error is upper bounded by the training error plus this guy. Right? So see that this guy is actually determined by both number of training examples, the confidence level, and the VC dimension, which reflects the complexity of your hypothesis space where you conduct learning. Right? So actually, if you do some simple mathematical derivation, right, calculate the gradient, you'll find that the larger the VC dimension, the larger the term. So this term is actually monotonically increasing along with VC dimension. In other words, right, if you want to tighten the bound, you need to increase the VC dimension. Means that you need to make your hypothesis space to be simpler, to be smaller, to be less expressive, right? It again justifies the Occam's razor's principle. So from the results, from the discussion so far, right, we can say why computational learning theory, right? Why it is important, right? It's not only in that we can give some more insightful analysis or expectation about the performance for some particular type of learning algorithm. It also can raise some interesting questions that lead to powerful learning algorithm, right? One prominent example is the boosting, right? So as we mentioned, right, either boosting or its variance, we're motivated by a theoretical question, right? If a concept class is weakly learnable, mean that okay, I can use some weak learning algorithm like decision stump to learn this concept class, which can perform only slightly better than chance, right? It's better than throwing a coin. And then the question is that if this particular type of target functions can be learned by some strong classifier, right? And that leads to, or that stimulates the invention of the ADA boosting, right? And similar here, right? By integrating the VC dimension into our agnostic learning case, right? We can derive a probabilistic bound with high probability. The true error of your learned hypothesis is upper bounded by the training error plus some term determined by the VC dimension and also the confidence level, right? A natural question is, can we use this to develop a learning algorithm? The answer is yes, and that's what we're gonna talk about right now, right? So we'll see that in the next topic about learning linear classifiers. We're trying to come out a learning principle that tighten this bound or make this bound to be as small as possible so that we can expect the true error to be small. So this learning principle in general is called structure risk minimization principle. Why is it called structure risk minimization? Because this bound has some structure, right? It can be decomposed as a summation of training error plus some term determined by, the VC dimension reflects your complexity learning hypothesis and other terms, right? This is called structure risk minimization principle, right? We want to minimize this bound to make your true error to be as small as possible. Right? So the particular algorithm we're going to talk about under this principle is called support vector machine. Maybe you haven't heard many times or in different areas, but support vector machine indeed is kind of a dominant approach in past 2 decades. Right? It was invented or it was proposed about 30 years ago in 1990s, and and then it brings kind of a storm. It's kind of like a paradigm shift approach. At that time, people are kind of focusing on all kinds of neural nets, all kinds of backpropagation algorithms. At that time, like SVM, small vector machine, is kind of killing. It's kind of queued, has been able to queue neural networks for 20 years or 30 years. Right? But it's kind of things are becoming cycle, right? Right now, neural networks come back and performs even better, right? In many applications, especially when our data is very large. But that does not mean support vector machines do not work well. Actually, SVM is also one of the most important baselines in almost all the machine learning applications. The reason is simple: support vector machines can do very well on small data set. It can be theoretically justified very elegantly. We'll see that later, and also perform well. Like it performs very well. It is much easier to tune than neural networks. It doesn't require too much data, right? So actually, you see that in many practical applications, if you don't have too much data, you don't have too many computational resources, support vector machines will still be the first choice. Okay, any questions so far? We're gonna enter a new topic.
Yeah, so I'm still a little confused on how we compute the VC dimension of an infinite hypothesis space. Do we have any methods besides what we did for linear classifiers of just plugging in 2 points and seeing if 2 points is shattered and then plugging in 3 points and so on?
Yeah, they do have, but we're not covered in this class.
Okay.
So what everybody is requested to understand is just to follow the concept to verify and calculate step by step. But of course, if you want to calculate the VC dimension for more complex classifiers like neural networks, like 1 nearest neighbors or 2 nearest neighbors, if you just check it step by step, it won't be sufficient, right? You must use more advanced techniques. We're not gonna discuss about that in detail. This is not our focus.
Okay, perfect. Thank you.
Okay. Our requirement is just for everybody to truly understand the definition of VC dimension. That's it. Okay. So now let us.
So is it VC dimension a very general, a very hard kind of constraint on an algorithm?
What do you mean by constraint?
Like VC dimension says that a linear algorithm, so if it is linearly separable, can have infinite number of samples which will be shattered. But VC dimension only says that the linear algorithm, a plane, will only be able to shatter probably 3 points. So isn't that a very hard constraint on the algorithm that we are basing that the difference between training and true error is a function of VC dimension?
No, so don't need to. So VC dimension is actually has you don't need to bind it to some particular type of classifiers like linear classifier. VC dimension can be defined on any classifiers, nonlinear classifiers like neural networks, nearest neighborhoods, and any other classifiers. It's not particular pertinent to linear classifiers. And you see that in computational learning theory, there are kinds of VC dimensions, kind of fundamental concept used to bound or analyze the complexity or expressiveness of all kinds of linear, all kinds of classifiers, not only limited to linear classifiers. But here, I just want to see that there's kind of like direct association between the linear classifier and the VC dimension and support vector machines, because the support vector machines are kind of like stimulated or invented based upon this bond in terms of VC dimension.
So I guess to put it in another way too, wasn't the really it seemed like to me you said the motivation for really coming up with all this theory is in the case when the cardinality of H is infinite.
Yes.
And so really now this inequality that we've derived for calculating the number of examples we need to guarantee some certain error with some probability, that all breaks down because now we're taking the log of this infinite number. And so we basically took a paradigm shift. We now have another way of representing that hypothesis space by using the VC dimension, and now we have an equation that's actually going to work based on the complexity rather than just the size of the space. So that's kind of really the motivation for all of it, right?
Yeah, of course.
Okay.
Yeah.
Cool.
Yeah. Does that make sense? Any other question regarding the motivation and the connection between this dimension and other linear classifiers or nonlinear classifiers? Okay, great. So basically, as Jordan said, right? So the motivation in theory perspective, right? This dimension is just is to define it. The motivation of this dimension is to represent or characterize the complexity or expressiveness for some infinite hypothesis space, because we cannot take logarithm size of it, right? And from the practical perspective, right, you see that for a particular type of classifiers, namely linear classifiers, based on the VC dimension and also the generalization error bound, we can derive a type of powerful learning algorithms called support vector machines, which we're going to discuss right now. Okay, so let us continue. So we're gonna look at the next bunch of slides. Okay, so can everybody see the slides? The new slides?
Yeah, and the transition looked good.
Okay, great. Yeah, I'm happy that today it does not stuck there. Okay, so our next topic is about support vector machines, right? So, but before we talk about support vector machines, let us look at the big picture, right? We want to arrange what we have discussed so far into a very organized way, right? We do not want to make them like out of order, right? It looks a mess, right? We want so the big picture is like this, right? So right now we're talking about linear models, right? In particular, linear classifiers. Right? So how can we define the learning algorithm or develop learning algorithm for linear models? Right? How can we develop a learning algorithm for linear models? Right? So a commonly used criterion is to evaluate how good the learned model on training data or on some future unseen data. The very first example of the learning algorithm is perception, right? Which we have just finished, right? So the perception is essentially a mystic-driven learning algorithm. So just to look at if you can correctly predict the incoming training example, right? If you make correct prediction, you do nothing, right? You just look at next example. You only update the model when you make a mistake, right? And then you adjust the model to correct mistake or at least improve the model, right, in predicting that particular example, right? So you do it again and again until you don't make any mistakes at all, or you have reached the maximum number of the updates. So this is the first example, right? So we define the goodness of learned model in terms of if they can well predict every training example. This is perception. But here we're gonna talk about another type of method, right? we use some computational learning tool, right? Plus the training error. Based on PAC principle, based on agnostic learning principle, we know that, okay, our generalization error, it can be upper bounded by the current training error plus some term, right? That term is determined by number of training examples, determined by the VC dimension, all kinds of stuff, right? So we use that bound to measure the goodness of the learned model. And our goal becomes minimizing that kind of bound. So this is called the risk minimization principle. So risk is essentially the bound. And this particular concrete example for risk minimization principle is support vector machines, which will span our quite a few lectures. And of course, under this design idea, right, we can design our learning algorithm in terms of how good a learned model, right, and adjust it to make it better and better, right. We can propose other measurement or evaluation procedure, and then use that evaluation to guide the training of your model or guide the search of your hypothesis. This is a big picture. So regarding support vector machines, what will we discuss? So first, we're going to talk about the philosophy or the goal of support vector machine training. Right? You'll see that our training is essential to maximize the margin for the linear classifiers. Right? And then we're going to theoretically justify why maximizing the margin will lead to small generalization error bounds, or in other words, small structural risks. And then we'll formulate margin maximization as the objective function. Right? Then the training becomes minimizing that objective function to find optimal weight vector and bias parameter. And then given this objective function, we'll talk about how to solve that. We will actually talk about in the primal formulation of SVM objective. We can use the stochastic subgradient descent, which is kind of variant of stochastic gradient descent. And finally, you see that how can we convert or extend support vector machines to nonlinear classifiers using the trick we have discussed before. Right? We talk about for linear classifiers, right? We can first conduct nonlinear feature mapping over the input features, right? And to map the existing feature vector to another feature vector, right? And then in a new feature space, we expect that we can find a linear classifier which will separate positive and negative examples. And then in a nonlinear extension case, to perform effective training, right, we'll need to know what is the dual form of support vector machines and where can we plug in the kernels, nonlinear kernels in the dual form, and how can we estimate that, right? And then in the dual form, we'll look at the classification hyperplane. You will see what does it mean for support vectors. So why this type of learning algorithm is called support vector machines. Okay, so this is a brief outline about this topic. Of course, this won't be finished in one lecture. It will actually covers quite a few lectures. So first, let us look at the goal of the training in the support vector machine. So as we just mentioned, right, we claim that the support vector machines was motivated by the generalization error bound in the agnostic learning setting, right? So the bound is here, right? So we can derive that. Suppose we have M training examples, right? Then with probability 1 minus delta, the true error of your learned hypothesis H can be bounded by the following upper bound, right? So the true error or the generalization error has a very large chance to be less than or equal to the training error plus this term determined by the VC dimension. Right? So first, you can see that, okay, if we simply increase the number of training examples, this bound will be tighter, right? Or this bound will be smaller. And so that the generalization error is expected to be small as well. Right? So this is very reasonable. The more you increase the training data size, right, you can expect the generalization performance will be improved as well, right? This bound justifies our intuition, right? But a more important observation is regarding the VC dimension. If we take the derivative of this term, I mean the numerator in terms of VC dimension, we will see that actually the derivative is always a positive. Meaning that you increase this dimension, you increase the bound, right? You increase the bound, meaning that the more likely your generalization error is big, right? On the other hand, low VC dimension gives tighter bound. Right? Given the same training error, I suppose you have a bunch of hypothesis spaces, right? Suppose they all can give you the same training error. And which hypothesis space would you like to choose? Any thought? By looking into this bound. An idea? Suppose I have a 10 hypothesis spaces, right? By using any hypothesis spaces, we'll give the same training error, say 0.01, right? And then which hypothesis space would you like to choose?
Where the whole generalization error will be less.
Yeah, of course. I mean, but
so
which
dimension is directly proportional.
Yeah, I think you catch the point, but I wouldn't say it's proportional because this is a nonlinear function. It shouldn't be proportional. But anyway, we should choose the hypothesis space with the smallest VC dimension, right? Or lowest VC dimension. Why? Because the lowest VC dimension gives the smallest term here, right? Meaning that it gives the smallest upper bound of the generalization error, right? So you can expect that the generalization error will be small as well. And then it naturally comes out, we naturally can come out kind of idea, right? We want to search our hypothesis in some space which has VC dimension to be as small as possible. Now let us look at if this idea can be applied to linear classifiers. The problem is that, or the bottleneck is that, if we directly apply this idea for linear classifiers, it won't work. Why? Because we know the VC dimension for linear classifiers. For general linear classifiers in d-dimensional input space is d plus 1. If we're going to search over the entire range of linear classifiers, it won't improve any. It won't improve the generalization error bound because the VC dimension is fixed. And then how could we address that problem? Or any thought?
Is there some way that it would be possible to do like dimension reduction, like some sort of like, I don't know, like reformulating the dimensions so you have less, I guess.
Yeah, that's a brilliant idea. Yeah, of course. You can consider that you project the instances into a lower dimensional space, and then you search over linear classifiers because this dimension is reduced, right? If you can maintain the same training error in a low dimensional space, you kind of like reduce the generalization error. Right? That's an excellent idea. That's very excellent idea.
But isn't that counterintuitive? We are increasing the projection space by adding nonlinear features, and then we are downgrading them to actually fit the VC dimension.
Yeah, that's another angle. Actually, you're saying, okay, if I add in nonlinear features, you kind of like reducing the training error.
Okay.
You're kind of reducing the training error, but at the same time, you might also increase this term because adding some nonlinear features may lead your search space to a more complex hypothesis space, right? And you have an increased linear classifier. So actually, I don't know if this trade-off can finally lead to a tighter bound or looser bound.
Okay.
But anyway, I think the idea from Michael in high level is right? But here, let us just put actual restriction. It's kind of cruel restriction. We cannot do any dimension reduction. I will just search the hypothesis in the original input space. How can we improve the generalization bound? Right? How can we improve the generalization performance? The idea is the same, right? The direction is the same. We want to reduce the risk dimension, but how? So the key is here. So the VC dimension for general linear classifier means that, okay, you're going to search the entire possible linear classifiers, right? Entire set. Right? So suppose in this D-dimensional space, right, these are all linear classifiers, right? Of course, the VC dimension is fixed. It's D+1. We know that. But what if I restrict the search range? What if I just pick up a small subset of linear classifier as our hypothesis space, right? And then we can expect, of course, the subset of linear classifiers, of course, its expressiveness is much less than the entire all possible linear classifiers, right? And if in the meantime, right, we can also ensure in this restricted set of linear classifiers, we can achieve same or similar training error. Then we tighten the bound.
So it's kind of like fixing the second term and finding the best solution for the first term using the constraint on the second term.
Yes. And to reduce or to decrease the second term, we need to reduce this dimension. We assume the number of training examples is here, is fixed. Right? We need to reduce the size of, we need to reduce the complexity of your search space. Right? In the linear classifiers, our strategy would be just pick up a subset of linear classifiers to search over, rather than search over the entire all possible linear classifiers.
So this relates back to Occam's razor, finding the simplest explanation, kind of.
Yeah,
right?
Of course. Yeah, this is actually, you can view it as like, I'm trying to fulfill the Occam's razor principle.
So in this example, right, if we want to have a subset of linear classifiers, would that be like we just ignore one feature and so we lower the dimensions by one?
Oh no, it's we still want to operate in the original input space, meaning we do not assume, okay, we perform some dimension reduction. All the inputs or examples still stay in the D-dimensional space.
Okay, so then how would we get a subset in the way that you said?
Yes. That's the key problem we're gonna address right now.
Would like ignoring features or lowering the dimension, right? Lowering the dimension seems like it would lower the VC dimension, and therefore, right, you would get a smaller hypothesis space.
Yeah. I'm not denying that possibility. I mean, that's a good idea. That's a brilliant idea. That's all. Of course, that's a choice, right? That's why like dimension reduction techniques is very popular in machine learning applications as well, because they can be justified in this way as well. Right? You can perform some dimension reduction, and in a low dimensional space, your VC dimension is reduced. At the same time, you can maintain the same training error. Then you tighten the bound to get the smaller true error, right? That's right. But
Gotcha.
here, I'm talking about a more rigorous case where we do not assume we can reduce the dimension. We just maintain the same dimension for the input space.
Okay, and so then then I guess I'm still curious about the subset stuff, but I assume you'll get into that.
Yeah. Well, we're gonna talk about that. Right? So and in that case, right, if we do not reduce the dimension, we still want to reduce the VC dimension. How can we do that, right? A realistic strategy will be, okay, just to pick up a subset of linear classifiers, right? A subset of linear classifiers, of course, the VC dimension can be reduced, right? Then the question is, which subset of linear classifiers should we choose, right?
Mm-hmm.
So that brings us the concept we mentioned before, right? Margin. Right? We'll see that we're going to use margin to index different subsets of linear classifiers. So first, let us recall the definition of margin. Right? When we say a hyperplane has some margin for a particular data set, it implies that, okay, this data set can be separated by this hyperplane, right? Like this data set, right? And then we can calculate the minimum distance between the data points and this hyperplane. This minimum distance is called margin, right? So previously, we give some intuitive explanation, right? So suppose this data is linearly separable, right? We might have like infinite number of separating hyperplanes, right? And which hyperplane do we believe will perform best in the future? So looking at these two hyperplanes, H1 and H2, right? Both hyperplanes well separated all the examples, right? Zero training error, right? And when we discuss, right, everybody knows, right, very good intuition that H1 will perform better. And the reason is that because H1 is farther away from the positive and negative examples, it can avoid going through the high density regions of positive examples. As a result, right, it will avoid the risk that some positive examples appear in the other side, right? On the contrary, if the separating hyperplane H2, like H2, right, going too close to the training examples, it is likely to pass through the high density regions, right? So, for example, these are the high density regions for positive examples, right? So when you predict some future example, if that example is positive, it has big chance that this example appear here, right? Because this high density region. That means H2 will have much bigger risk to give wrong prediction. And similarly, because it passes through the high density region for the negative examples, right? When you make a prediction for future negative example, it has high probability the negative example appear here, right? And H2 makes a wrong prediction as well, right? On the contrary, H1 will have a much smaller risk. Why? You can now imagine that if a positive example appear at here, the chance is very low. Why? Because this is a low density region, right? If a future example appears to be positive, it's more likely to show up here, right? There's ellipsis region, right? It's unlikely to show up here. That means H1 has a much smaller risk to give wrong prediction, right? So give this intuitive explanation, right? And explain that and advocate that we should favor large margin linear classifiers, right? But how do we justify this in terms of computational learning theory in agnostic learning setting? So we're going to introduce the so-called data-dependent VC dimension, right? So as we mentioned, right, previously, if we search over the entire linear classifiers, all possible linear classifier, the VC dimension is fixed, it is D+1, right? But now let us try to index different subsets of linear classifiers in terms of margin for a particular data set. Right? So we can consider two margin values, gamma 1 and gamma 2. And gamma 1 is bigger than gamma 2. Right? So then we define the subset of linear classifiers H1 as linear classifiers that have a margin at least gamma 1. Right? It's bigger than or equal to gamma 1. Right? And we can also define another set of linear classifiers, right? H2, which have a margin at least gamma 2. Right? And of course, because all those linear classifiers, they have margins, meaning that, okay, they can separate positive and negative examples, meaning that their training error is zero, right? And from our intuition, right, from our analysis from this figure and from our intuition, we believe that the entire set of functions H1 is better than H2. Why? Because the margins of the most linear classifiers in H1 is bigger than H2, right? We believe that they're going to predict better for the future of same examples. If we convert this into a computational learning theory statement, right, we're actually saying that, okay, if you search over linear classifiers, if you search linear classifiers over H1, the generalization error bound should be tighter or smaller than you search linear classifiers in H2.
But the margin of a data set is like pretty hard to find, right?
Yeah, of course. We haven't gone to the practical step, right? We just do the analysis. Does it make sense? Of course, we're not trying to identify the margin of the data set, right? We're just saying, okay, suppose I can pick up, given this particular data set, right? So I can define a subset of linear classifier H1, another subset H2, right? And H1 is defined as all the linear classifiers whose margin for this data set at least gamma 1, right? H2, gamma 2, right? Now, from our intuition, we believe that, okay, H1 is generally better than H2, right? If we want to restate this intuition in terms of computational learning theory, right? We're saying, okay, we actually believe that if you learn your hypothesis or learn your linear classifier by searching over H1, we expect the generalization error bound will be smaller than the bound when you search over H2. The question is that our belief true? It is true. It is true, and it is justified by a very important theory provided by Vapnik. So again, he's the inventor of Slovak machine, right? This theory gives an upper bound about the so-called data-dependent VC dimension. So in general, we can use our training set and a gamma to define a subset of linear classifiers denoted by H. So H consists of linear classifiers that separate the training set by a margin at least gamma. And then we are curious to know what is the VC dimension of this subset of linear classifiers H. So we can upper bound the VC dimension of H by this guy. So it's minimum of R squared over a gamma squared and D plus 1. Right? So D is the input dimension, and R is the radius of the smallest sphere containing the data, meaning it's actually the maximum span of the training instances in this training set. So this R has the same meaning as in our perceptronistic bound. And gamma is the margin, right? Is the margin which index H, right? And D is input dimension plus 1. From these theorems, we can see that, okay, the larger the gamma, right? The larger the gamma, the smaller the upper bound, right? And then you can expect the smaller the VC dimension of the corresponding H. Right? So now we build up a connection between the margin, VC dimension, and the generalization error bound. Right? So we can infer, we can reason about that like this, right? If we can have larger margin, right? The corresponding set of linear classifiers will have a lower VC dimension, right? If you search over that hypothesis space, right, you're gonna get a smaller generalization error bound. Then we expect that we have a smaller generalization error. That's the logic chain, right? We use margin to index subset of linear classifiers. And if we search over a subset of linear classifiers which correspond to a larger margin, this subset of linear classifiers has lower VC dimension, and this lower VC dimension will further leads to a smaller generalization error bound. So a natural question is, why not? We know that the smaller, the larger the margin, the lower the VC dimension, the tighter the generalization error bound. Right? Why not we just choose H to be to correspond a gamma that can be as large as possible. For this particular data set, we can choose an H such that it corresponds to the largest gamma we ever had, right? Of course, it's hard to compute. Right? But if we can ensure that H corresponds to the maximum margin for that data set, for all the separating hyperplanes for that data set, right? We kind of achieve the smallest VC dimension possible. Right? And then we kind of, we expect that we can achieve the smallest or the tightest error bound, and we expect that, okay, our true error will be small. This leads to our learning strategy in support vector machines. We're trying to find linear classifiers that maximize the margin. When you do this training, right? When you do this action in the learning procedure, you're essentially trying to search the linear classifiers in such an H whose margin to be the maximum. Meaning that, okay, you're gonna have your H, the hypothesis space H you search over has the smallest VC dimension, and then you have a tightest lower bound, and then you give the best generalization error. That's how this learning strategy in support vector machines was motivated. Any questions so far? So the importance, the key to understand how this learning strategy, right, is follow this chain, right, follow this logic chain, right, and just depends on our generalization error bound on the agnostic learning result. Okay, so now suppose we have a now suppose, right, we're now very clear about our learning strategy. We want to maximize margin, right? We found linear classifiers which has the largest margin, right, as large as possible, right? How can we formulate this principle as a actionable objective function, right? Such that we maximize or we optimize this objective function is equivalent to minimize or maximizing the margin, so that we can find optimal model parameters, including weight vector and bias parameter B, right? So we'll next talk about how this objective is formulated, right? So we need to review the geometry of linear classifiers. We know that the classification boundary can be represented by this equality, where the prediction score is 0, right? And also, to calculate the distance between an arbitrary point and this classification boundary is to just calculate the absolute value of the prediction score over the norm of the weight vector. Right? This is just the formula, right? And a very important property for linear classifier is that we only care about the sign of the prediction score, right? Not the magnitude. In other words, we can skew B, W1, W2 arbitrarily, right? By 0.1, 0.01, 0.001, or 1 billion. That doesn't change the position of the separating hyperplane, meaning that all those setting of B, W1, W2, they are equivalent. Right? They correspond exactly the same linear classifier. This is very, very important in the formulation of the SVM objective. And we'll see later. So now, let us first come out a naive formulation. Right? So first, we start off from the definition of margin. Right? Margin is the distance of the closest point from the hyperplane. Meaning that if you want to calculate margin for the current hyperplane, I'm gonna go through every training example, right? Each xi and yi, I calculate distance because xi and yi can be correctly predicted, right? Otherwise, it won't. The classifier don't. The hyperplane doesn't have the margin, right? So the numerator can be represented as yi times this prediction score, which is always a non-negative, right? And then divided by the norm of w, right? And then our goal is to maximize this gamma. Right? So now we can say the naive formulation of the objective is essentially a max-min problem. Right? In the inner part, we need to go through every training example, and calculate distance to pick out the smallest one as the margin. In the outside, we maximize this margin in terms of WB. Right? In the inner part, WB is fixed, right? We just vary the number of training, vary the training examples to look at the smallest distance, right? So the original definition of margin is usually referred to as geometric margin, right? Why? Because it just corresponds to the original definition, right? But more frequently used is the so-called functional margin. So what is functional margin? Functional margin is just the minimum value of the numerator. Because this minimum is only determined by the numerator rather than the denominator. Why? Because the denominator is just the norm of W, right? And it does not contain any data points, right? So if you want to find the minimum of margin, you just find the minimum of the numerator, right? So we call the minimum numerator as the functional margin. So what's the problem of the original formulation? The problem comes from the computation. So this is a max-min optimization problem. So if you know something about optimization, you know that this max-min or minimax problem is really hard to solve because you're looking for you're not looking for local minimum. You're not looking for local maximum. You're looking for the so-called saddle points. Right? Your gradient is 0, but it does not belong to local minimum. Does not belong to local maximum. And even worse, every time when you change WB a little bit, right? You're gonna going through an inner minimization phase where you need to go through every training example and calculate the distance again and pick up the smallest one, right? So you can imagine the computation is very, very expensive, right? So how can we simplify this? Right? How can we make it more easier? How can we make it more convenient and easier to deal with? Right? Here it comes a very important observation. We know that for any linear classifier, oh, by the way, any questions so far? I want everybody to be on the same page in the original, in the naive formulation of SVM objective. Is everybody good? Okay, yeah, that's perfect. So as we just mentioned, right, performing this max mean optimization is kind of costly, right? We want to simplify this objective. How? We need to use an important property, right? Notice that for linear classifiers, right, we only care about the sign, not the magnitude. Meaning that for arbitrary set of B, W1, W2, you have an infinite number of the equivalent settings of B, W1, W2, right? You can multiply B, W1, W2 by 0.1, 0.01, 1 billion, 1 trillion. They are all equivalent. Right? That means it seems unnecessary, right? Or we have the freedom to scale up and down the W and B. Right? That means it's unnecessary to just search all possible W1, W2, and B, right? We can just restrict the range of the search for W1, W2, and B into a very small subset. Why? Because there are so many duplications, right? Duplications, I mean, they are essentially correspond to exactly the same linear classifiers. It's not necessary to go through all of them, right? And then how can we restrict the search range, right? We can just restrict the range for W and B such that the numerator, the functional margin, is always 1. In other words, restrict our W and B such that this minimum of the numerator over the training data is always 1. The benefit is that, okay, now that I know, okay, this minimum part is 1, right? The margin, the geometric margin will now only becomes 1 over the norm of W, right? So we just perform an outside maximization. We do not need to perform inner minimization to go through all the data points because I put the prerequisite that I require the minimum functional margin is 1. The minimum numerator, or in other words, function margin is 1.
How are you accomplishing that again? Trying to lock it into being 1?
Yeah, I try to lock it up being 1. I try to lock the minimum value of these numerators across the training data points to be 1.
Right, so this is the minimum distance between our line W and the point X, right? Or the point.
So it's not minimum distance. It's actually just the minimum of this product. It does not divide. It is not divided by norm of W.
Okay.
Right? I just make an extra restriction. Like I want this minimum of W transpose Xi plus B is always 1. actually, I mean, initially we feel like it's kind of like might restrict the effectiveness of the learned WB. But after some thought, you say actually this is totally equivalent to search over the free WB. Why? You can imagine like for arbitrary value W and B, right? You can choose arbitrary value W. Suppose we do not impose any restriction. Right? And of course, according to W and B, you can calculate the functional margin, which is the minimum value of this product, right? In the numerator, right? Yi W transpose Xi B, right? And now, if I just divide WB both by that functional margin, namely this minimum value, right? I immediately get an equivalent set WB, which has functional margin to be exactly 1. So putting this extra restriction does not make you miss any possible optimal WB. And the benefit is obvious because now that we know the function margin here is 1, right? We do not need to perform inner minimization, which you need to go over every tuning example, right? To calculate something and pick up the minimum. So this is a key idea. Any question regarding this simplification?
So yeah, so I guess to restate that, so what we're saying is, so y and x are fixed. If you go back to the functional margin, yeah. So y and x are fixed, and so then if we basically say then this whole product, the functional margin is restricted to be 1, that's going to give us some subset of w and b that's going to satisfy that. And that's what we're working. And then, so we're just saying we're going to start with that. That's going to give us some subset of linear classifiers, and then we're just going to maximize over that.
Yes, exactly. Okay. Exactly.
Cool.
Yeah. And the amazing part is that, okay, even you restrict WB in that small subset, right? You actually won't miss any effective optimal WB. Following the logic I just presented, right? For any WB outside this subset, right, whose functional margin might be not 1, might be bigger than 1, might be smaller than 1, it's fine. But you just divide WB by their own functional margin, you get an instance of WB in that subset whose functional margin is 1. And they are equivalent in terms of classification.
I see. Thank you.
And another question, because it's really important to understand why should we formulate SVM in that way. Okay, great. So now let us just summarize our idea, right? So this is the naive formulation of SVM learning, right? So we define the margin according to the original definition, right? Some minimum distance between every data point and hyperplane, right? And then we want to maximize the margin, but this is a max-min problem. It's costly. It's not easy to solve. And then we utilize the property of linear classifiers that we only care about the sign of the prediction function, right? And we do not care about the magnitude, so that we can restrict the WB such that the functional margin, the minimum value of this numerators is just V1, right? And then our problem is just to maximize 1 over the norm of W, because we know that the numerator, the minimum of the numerator is simply 1. And next, we can formulate the learning problem as a constraint optimization problem. So first, if we want to restrict our functional margin to be 1, it basically says, okay, the minimum of those yi w transpose xi plus b to be 1 And then that means, okay, for every training example I, this yi w transpose xi plus b is no less than 1, right? This is our constraint. That's how we restrict the WB in a smaller space, right? And for the actual objective function, because we know the function margin now is 1, right? So we're actually maximizing 1 over the norm of W, which is equivalent to minimize half of the square norm of W. Right? Half of square W norm is to say half W transpose W. So now it's clear, right? So the objective is to minimize half W transpose W. This is just for convenience, to calculate gradient, whatever. Also, the half is used to cancel the factor when you take the gradient. It's the same. It's the same motivation as we do the linear regression. So we minimize this, give us maximum 1 over the norm of W, which is correspond to maximizing the margin, right? And those constraints actually restrict WB to ensure that the minimum of the function, the minimum of the numerator, namely the function margin, is 1. So this is called hard support vector machine. Why is it called hard support vector machine, right? We actually require the data set is linearly separable. And as we mentioned before, right, we know that if all the data points, if a data point can be correctly predicted by a linear classifier, then this product will always be non-negative, right? But here we can put an extra constraint. Our constraint is even stronger, right? We want this product to be no less than 1. Right? And we'll look at how to solve this optimization problem later, right? But here, hard SVM is insufficient. Why? Because we cannot always assume the data is linearly separable. If it's data linearly separable, well, everything is good. Right? But what if the data is not linearly separable? In that case, how can we formulate SVM objective, right? By excavating the same kind of idea. If the data is not linearly separable, well, we cannot guarantee for every example this inequality will be satisfied. Right? Because some example is always wrongly classified, meaning that this product can be less than 0, right? If you solve hard SVM on inseparable or non-linearly inseparable data set, you give you will end up with an infeasible problem, and the solver will report you no solution, right? And how can we address this problem, right? So the idea is that when the data is not linearly separable, right, we're trying to automatically find a subset of examples. And this subset of examples, we believe they can be linearly separable, and we want to maximize the margin of the hyperplane for that particular subset of examples. Of course, the remaining minority examples might be incorrectly classified by this hyperplane. In other words, we'll allow some example to break into the margin. Like in this case, we have positive, we have negative examples, but they are not linearly separable. If you're trying to find a line which can perfectly separate all the positive and negative examples, you won't be able to find that. Then our goal is kind of like a step back a little bit. We want to find a subset, a majority subset of the examples which are linearly separable, right? For this, that includes this part and this part. Right? For this for the majority set of examples, they are linearly separable, and we want to find a separating hyperplane with the largest margin for them. Meanwhile, we allow some outliers, very small number of outliers that can break into the margin. So you see that for this particular hyperplane, right, the margin is for the most examples here and here, right? But we have two outliers here and here. For these positive examples, of course, it breaks into the margin. For negative examples, it not only breaks into margin, right? It actually comes to the next side, right? That's the idea for learning SVM in nonlinearly separable data, right? But how do we formulate an objective function, right, to achieve such kind of a result, right? Can automatically identify, okay, which majority set of examples are linearly separable. So I found so that for which I can find a large margin classifier, right? So here's how we formulate the soft SVM, right? So we're gonna introduce a slack variable CI for each example. Then in our constraint, we no longer require this product of function margin, not function margin. This product is no less than 1. Right? We relax the constraint by that yi w transpose xi plus b is less than 1 minus KCI, and KCI is non-negative. So you can see that if KCI is 0, then you return to the hard SVM, meaning that this example stays on the margin or outside margin. If KCI is strictly bigger than 0, that means xi and yi kind of intrude margin. And then we modify, in this way, we modify the constraint to allow a few examples to break into the margin. At the same time, in the objective function, not only for the term about margin, we also add a term which is the summation of those select variables and multiply by a constant c, right? C is hyperparameter represents some trade-off. This is how we formulate soft SVM. So now the question is, why would we add summation of select variables in objective for soft SVM? Why not we just remove this, right? We just modify the constraint like this, right? And in the objective function, we still minimize this half W transpose W, namely maximize the margin. Can we do this? I will leave it as an exercise, as a problem, a question for you. Like if you have time, just think about that. Right? And in the next lecture, we will give a more detailed explanation, like why in the soft SVM we should formulate our objective constraint like this. Okay, see you on next Tuesday.